So good afternoon, everyone, and welcome to our first seminar this year. It is an honor for us to have as our speaker today, Professor Carlo Massimo Casciola, for his talk titled Dynamics of Bubble Nucleation. Professor Casciola is based in Sapienza, University of Rome in Italy, and leads a research group of about 20 researchers, postdocs, and PhD students working on the fluid dynamics of complex flows with a chiefly theoretical and numerical approach. His research is oriented to fundamental and numerical modeling with substantial interactions to related neighboring disciplines such as engineering, physics, material science, chemistry, mathematics, biology, and medicine. Most of his research topics are characterized by the coupling of macroscopic flows with a microstructure. After being awarded an ESC Advanced Grant in 2013, a significant part of the research work has focused on different aspects of cavitation. For example, heterogeneous nucleation, wettability, bubble collapse modeling, bubble wall interaction. The tools employed span from direct and large eddy simulations to phase field models, free energy methods, and molecular dynamic techniques specialized for rare events. Significant contributions concern techniques and models for wettability and heterogeneous nucleation on complex surfaces, phase field methods for bubble dynamic cavitation, direct numerical simulations of polymer drag reducing flows, scaling laws and energy fluxes in homogeneous turbulent flows, particle transport in turbulent flows in the two-way coping regime. Recently, the research interest extended to the experimental aspects of bubble dynamics, cavitation, and microfluidics for application in biology and medicine. Professor Casciola, thank you very much for being our speaker today. Over to you.
Okay, thank you so much. So first of all, let me thank the organizers for this invitation, so for the opportunity to present this talk at the HPC National Competence Center seminar series. So it would have been a good opportunity to visit Cyprus, but unfortunately we are still stuck at home due to this COVID pandemics. So today I'm going to talk about dynamics of bubble nucleation. So let me first of all try to explain the title, why dynamics of bubble nucleation. So nucleation is typically a subject that is dealt with in the context of equilibrium statistical mechanics. What I intended to do was to try to set up a framework, a dynamic framework to study nucleation in interaction with macroscopic or mesoscopic flow. So for instance, if I may, okay. So what you should see here are a couple of videos showing examples of how nucleation can indeed be coupled or even triggered, in this case, the macroscopic fluid motion. In the top movie, you see that by triggering a strong explosive nucleation in a soda bottle, you are able to excite a very intense macroscopic jet, whereas in the bottom one, what you see is a usual boiling phenomenon through which you form bubble of vapor inside a hot water, and then you see that a very complicated fluid pattern may emerge. So the point is that as we see, nucleation can indeed be strongly coupled with macroscopic fluid dynamics, but the difficulty in doing that is the fact that nucleation is intrinsically a microscopic phenomenon. So here, in these two short animations, what I'm showing are results taken from molecular dynamic simulations of a simple metastable liquid. And then what you see is that all those small point particles, they are continuously moving due to thermal agitation. And then what it happens is that you are going to form regions which are depleted of particles. Most often, those regions are reabsorbed until the embryo of the bubble reaches a critical size or a critical dimension, after which you have an explosive formation of a vapor state. On the right panel, you see instead nucleation at the boundary. It is well known that contact of the liquid with the solid boundaries, and in particular with the geometrical or chemical discontinuity, they increase a lot the nucleation rate by acting basically as a sort of catalyst that splits the nucleation process into sub-steps with much lower free energy barriers. Okay, so the basic question I want to address in this talk is the following. Can we bridge the gap between the metastable liquid and the successive nonlinear bubble dynamic space encompassing nucleation in the model? So this is in principle a tremendous task, since nucleation starts at nanoscopic scales and we want to reach, I would say, mesoscopic or macroscopic scales, which in practice means in the simulation I'm going to discuss, we are reaching up to sort of 10 micron size bubbles. Okay, let me start from considering a system in equilibrium. Now, by equilibrium, I mean that the thermodynamic control parameters of the system, say the volume, the temperature, the chemical potential, or the mass of the system, they are kept constant during the nucleation phase. Now, one of the most important problems that we have in nucleation of bubble is, for instance, understanding the tremendous tensile strength of water. So what I'm showing here is a diagram showing, discussing an experiment done with quartz micro inclusions. Inside these cavities in quartz, you have water, and inside the water there is a small bubble. Then the quartz is subjected to a thermal cycle in such a way to first absorb the bubble and then cool it down until the bubble reappears. So by doing this kind of experiment, Copen and his group was able in 2012 to find that the tensile strength of water can go down to minus 120 megapascal, which is a tremendous negative pressure. Now, many experiments have been done in this context to find what is the limiting tensile strength of water, and they are sort of summarized in this diagram, in which you see as a function of the temperature of the water, the cavitation, the so-called cavitation pressure. So this cavitation pressure is defined in such a way that it is the pressure of the system at which the probability to observe at least one nucleated bubble is 1/2. So you see that the data points are considerably scattered throughout the diagram. So this scatter is mainly due to two different causes. One of them is the fact that there are technical difficulties with certain kind of experiments which make the data rather scattered. The other one is that bubble nucleation is intrinsically a stochastic process. So unless you're able to acquire a sufficiently large statistic about the nucleation process, of course, there is a significant scattering in the data. However, a message emerges clearly from this picture, and it is the fact that the cavitation pressure is enveloped from below by this red curve that is shown over there. So it means that there is a limit to the negative pressure that you can reach at given temperature before you can systematically form a vapor bubble. So the first question is, can we do simulations, or can we apply numerical methods in order to find out what is the limiting cavitation pressure for ultra pure water? So for that, we need, first of all, a model. Now we are dealing with a multi-phase system, so it is not an homogeneous system, and this means that the free energy of this object is going to be a functional of certain fields. In particular, for the problem at end, the relevant fields are the density field rho and the temporal theta. So the free energy of the system is going to be a functional expressed as an integral of a bulk free energy density, that object f at sub 0, which locally depends on density and temperature. And from that, we assume that we have an equation of state of some sort, for instance, a van der Waals equation of state or something else. And then to add to that, we add a term which is quadratic in the gradient of the density gradients, And this is done, it is there to penalize the formation of the interface between the liquid and the vapor. So this is the celebrated van der Waals square gradient approximation for the free energy functional of a multi-phase system. Now, for given thermodynamic conditions, so we fix the volume of the system, we fix the temperature and the chemical potential, the equilibrium state of the system is characterized by the Euler-Lagrange equations, which minimize the functional. And in this particular case, you end up with an elliptic partial differential equation for the density field, which is nonlinear due to the presence of the free energy, bulk free energy density. In general, this equation is rather complicated to be solved, and you need numerical methods and large computers in order to solve it. But in a simplified case in which we consider a one-dimensional system, the solution is sort of easy. It can be obtained by simple quadrature. And then if you apply suitable boundary conditions, say we assume that far to the left, we have the vapor state at low density, and far to the right, we have the high density liquid state, then the solution describes a transition layer within the low density vapor and the high density fluid, which describe the interface between the two phases. So this is a sort of diffuse interface across which you have a sharp increase in the density. So you have the sharp gradients, and then you have a significant contribution to the free energy of the system. This kind of model should be contrasted with what is called the sharp interface model, in which instead you see that at the sharp interface, you have a finite jump in the density of the vapor and the liquid, of the fluid in general. Okay, so once we had found our model, we could identify our two equilibrium or metal stable states. One, say, is the liquid, which is characterized by the density field rho A of X in this case. And the other one is the vapor, which is called rho B of X in this case. Now, if you have a transition from liquid to vapor for given temperature, volume, and chemical potential, it means that you have a sequence of density field that, starting from the liquid, they progress according to a certain progress variable that we can call S over here. You progress from the liquid toward the vapor. So in fact, what you identify is a path in the space of density fields, which connects the two metastable states, the liquid and the vapor. Along one of those paths, you can build a free energy profile. So at each given position S along the progress of the reaction, you have attached to it a value for the free energy. So you have F as a function of S, which we call the free energy profile. Then what we are interested in is what is called the minimum free energy path. So this is the particular curve such that the path is everywhere tangent to the free energy gradient. Now, the free energy is a functional, so the gradient basically is a functional derivative of the free energy with respect to the density field. And what we want to have is that the orthogonal component of this functional derivative to the path must be 0. So the problem to identify the mean free energy curve, which correspond to the most probable transition path within the two metastable states, you have to find out an algorithm to solve this. And this has been done. The algorithm is called the string method, and you may find more details in the review paper by Maragliano et al., published in the Journal of Chemical Physics 2006. In practice, what happens in discrete terms is that you discretize the density field such that your field becomes now a huge vector. So the free energy is now a scalar function of this huge vector. And then what you do, you evaluate the gradient of this free energy with respect to the discrete variables. You project it in the orthogonal direction to the path, and you pretend that this orthogonal projection is 0. For that, you need to relax your system towards the local minimum when you move in the transverse direction to the path. This thing is done by using this string method, which consists in building a curve in the space of the density field. Now, in the sketch on the left of the slide, what you see is an elementary case in which we assume to only have two independent variables, say rho 1 and rho 2. And then we have a curve in this space. We have a free energy landscape. And then we want to relax this curve in such a way that the initial point and the last point, the initial image and the last image along the curve falls into the two locally stable minima, whereas all the other images, all the other points fall down into the bottom of the canyon or the valley that connects the two equilibrium states. So this is, in a nutshell, a description of the string method. The interest in the string method is that in practice, the relaxation of each of the images along the string can be done almost independently from the others, and this allows to exploit the huge parallelism of modern computer systems. Okay, once you have found the path, the minimum free energy path, then you're going to have a free energy profile along the path. So what I'm plotting here is a sketch showing the free energy along the progress variable S along the transition. And in our case, what you find is that we have two locally stable states, the metastable state corresponding to the liquid and the stable state corresponding to the vapor. And then they are separated by a saddle point, which is the local maximum, the maximum that you see there, which is in fact a saddle point being a maximum along the path, but being a minimum in the orthogonal directions. So once you have this free energy profile, you can evaluate the barrier, that is the amount of free energy that you need to pass from the metastable liquid through the top of the barrier to fall down into the stable vapor. Then applying what is called Kramer's theory, from that you can evaluate the frequency through which the system initialized in the metastable state goes to the barrier. And from that you can determine what is the transition probability. From the transition probability, at changing the thermodynamic condition of the system, you can identify the condition for which the probability of observing the transition is 1/2. And from that, you extract the cavitation pressure. And then this is what you find. In fact, the red curve I was showing in the previous slides is in fact our computation, which matches remarkably well the experimental data by showing that it in fact consists in the lower envelope that you have of all the data available from the literature. So this shows that by using this kind of model, which was originally introduced by van der Waals, and then keeping the system with modern rate event techniques for studying transition, you can indeed find what is the reasonable approximation for the cavitation and pressure in water, which up to recent times was considered a completely open problem. Now, once we have sort of set up our problem in terms of equilibrium conditions, let's move towards the dynamics. So for considering dynamics, what we actually need is basically a deterministic description of the system in which we have to include information concerning the change of state, liquid, vapor, vapor, liquid, and so on, which should be described in such a way to account for the latent heat. We need to include nonlinear effect that we know arise in fluid mechanics, so in the compressible Navier-Stokes equations, for instance. And on top of that, we should add information concerning the thermal fluctuation. So from the molecular dynamics, we have seen that the nucleation process is triggered by thermal fluctuations. So if we want to build a mesoscopic dynamic model encompassing nucleation, of course, we need to endow the system with the appropriate system of thermal fluctuations. So let me start from the deterministic part. So we are going to have a mesoscopic or macroscopic system in which we have the fundamental fields of mass density, macroscopic velocity, and energy density. So you have to write mass, momentum, and energy conservation equations. Those are the standard ones that, for instance, you may use in compressible fluid mechanics, in gas dynamics. Here, the main difference is in the constitutive equation for the stress and the energy fluxes, in which they should take into account the fact that the system is a binary system with two different phases, and there is an interface across which the density changes abruptly, and the presence of this sharp change in density across the interfaces introduces distributed capillary stress, which overall accounts for the surface tension that the macroscopic model, sharp interface model, are taken to describe the interface between the liquid and the vapor. So basically, for instance, the stress tensor that appears both in momentum and in the energy equation consists of a part which is sort of the standard Navier-Stokes part, so the pressure plus the typical dissipative Newtonian contribution. And in addition to that, there is the part which is framed in blue, which corresponds to this distributed capillary stress. So if you take an overall look at this equation, you see that they are terribly nonlinear, because on top of the standard nonlinearity of the compressible Navier-Stokes equation, you also have important nonlinearities associated with the density gradients. Nevertheless, once you have built a thermodynamically consistent continuum model for this process, what you can do, you can discretize this equation, put them on a sufficiently big or sufficiently large computer, and see what happens. So in particular, what I'm going to show here is an animation taken from a numerical simulation in which we have a bubble, an initially spherical bubble, which is close to a solid boundary, the black wall in the bottom. And the collapse of this bubble is triggered by an incoming pressure wave, which is the black horizontal curve on top. Now let me animate the movie and see what happens. So the pressure wave goes down, the collapse of the bubble is triggered, and then something very complicated happens. In particular, due to the asymmetry of the system, what happens is the bubble collapse is asymmetric, and the top part of the bubble collapses faster than the bottom part due to the blockage of the wall. And as a consequence of that, you have a deformation of the bubble, a formation of a strong jet going toward the solid wall, which produces a hole in the bubble, which changes its topology from an initially spherical one to a toroidal. In the meanwhile, due to the bubble collapse, what happens is that the system, a complicated system of pressure waves, are launched in the liquid. So you see that this strong nonlinear system ended with phase transition, the possibility to transition from supercritical to subcritical state, and vice versa in the vapor, and so on, is able to describe a rather complex process that takes place when a bubble collapses near a solid wall. It is important to notice that those apparently innocent arrows that represent the velocity of the fluid, in fact, they are very, very fast. We are in presence of a strong compression wave. They are almost shock waves. So it means that the velocity of the fluid over there is of the order of the sound speed in the liquid, which, as you know, is rather high. So what you have is, in fact, that during the collapse, you develop very intense temperature and pressures and very strong impinging jet, which combined together are responsible for the damage of the material over which the bubble collapse takes place. Okay, now what we need to do is to take this model, this diffuse interface model, and complete it introducing thermal fluctuations. Now, we need a little bit of statistical mechanics in order to describe the proper way to introduce thermal fluctuation into the system. So let me start with the microcanonical system, that is an isolated system in which conserves energy in a given volume with a given number of particles. From that, elementary statistical mechanics tells us what is the equilibrium probability density of the microstate. So the microstate is the collection of position and momenta of all the particles of the atoms or molecules forming the system. And then what we do, we coarse grain this system, dividing it in cells. And we count the number of particles and the energy that we have in each cell, and identify a vector variable that we call collective variable, which is in fact a coarse-grained description of our macroscopic system. So we attach a density and an energy to each cell. And since we know the equilibrium probability distribution of the microstate, from that we can derive the probability that this coarse-grained value experience a certain fluctuation with respect to the equilibrium value for which the density and the energy is constant everywhere in the field. Now, if you do the explicit computation, what turns out is that this probability distribution for the fluctuation can be expressed as the exponential of the entropy of the fluctuation. This is what is known in statistical mechanics as Einstein-Boltzmann principle, and it says that the probability density function of a fluctuation is indeed a functional of the fluctuating field expressed as the exponential of the entropy. Now, the point is that how can we obtain a model for this entropy function? That can be done by taking the van der Waals diffuse interface model that I was considering before and expressing the entropy as the functional derivative of the free energy with respect to the temperature with a minus sign. If you do this computation, the result is an integral of an entropy density, function of the local density, mass density, and the temperature integrated over the volume occupied by the system. And as a consequence of that, now you have an explicit expression for the probability of a fluctuation given as the exponential of the integral of this entropy density, which is now completely defined by our van der Waals model, equipped with an equation of state for the free energy density of the fluid. Now, what you see here is an example for which that probability can be worked out explicitly. So the equations of state that I was using in this case is the van der Waals equation of state. And what you see here is the probability of having locally at a certain position in space a fluctuation in temperature and number density. So if you look at the shape of this ice or the surface, you see that this probability presents two distinct maxima. One of them, the largest one, corresponds to small densities, and it is the state which corresponds to the vapor, and this is the stable vapor. Whereas the other maximum, which is a relative maximum, a smaller one, which takes place at larger number density, that is the metastable state corresponding to the liquid. Now, with this kind of model, now you have an expression for the entropy, and once you have the entropy, what you can do, you can evaluate the correlation in the fields. So you can evaluate the correlation functions of the density at different place, velocity at different place, and so on. Velocity, 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 density, density, temperature, and so on. You see that what comes out is what is called in statistical mechanics, in theoretical physics, a path integral. So what you have to do, you have to average the product of the fluctuations. So the tensor product of the fluctuation with itself, multiplied by the probability, which is the exponential of the integral of the entropy. And then you have to integrate that over all the possible density, velocity, and temporal fluctuations. So this integral is called the path integral. Generally speaking, it's almost impossible to evaluate analytically, but in our case, we can play a little trick, which is to develop to write the approximately the entropy as a quadratic form of with respect to the fluctuation around the maximum. In this way, this path integral becomes a Gaussian path integral, which can be solved analytically. As a consequence, now we have access to the equilibrium correlations, density, density, temperature, temperature, velocity, velocity, and the mixed one, which are 0 in this case. And then we have a characterization of the correlation in the system. Why do we need those correlations in our case? The reason is that now we take our model, so our continuum equation for mass density, velocity, and energy, and augment them with stochastic terms. So we add a noise, which is a delta correlated in space and time white noise. That is called delta sigma and delta q in this case, and are the terms which are framed by the red square. So that they are, of course, they have a tensorial or vectorial nature depending on the equation, and the noise is multiplied by a suitable operator. It is an intensity operator, which in this present case is a divergence. And now what we pretend is that by forcing this system of equation with this noise term, we want to obtain the equilibrium correlation that we know should be there by statistical mechanics arguments. So this fixes the noise intensity operator and closes the system. So now we have turned our capillary Navier-Stokes equation with a stochastic forcing. So they are a sort of generalized Langevin equation. And now we can solve those Langevin equations. In particular, of course, we need special integration techniques because we need to be sure that the stochastic terms are treated properly. That is, they produce the expected correlations. And then once we have done that, we can implement, discretize those equations and implement them on a computer. And let's see what happens in this case. So what you see here is a triply periodic simulation in which we start from a homogeneous metastable liquid, and then we start up the fluctuations in the system, and you see that sooner or later vapor bubbles develop. The vapor bubbles develop. Initially they are very small, they are the nuclei, then they grow to be larger than the critical size of the nucleus, and then you see that we form larger bubbles. So we have, in a certain sense, we have succeeded in building a model which is able to start by itself the nucleation process, being endowed with equilibrium thermal fluctuations, which are consistent with the thermodynamic properties of the system. Now, if you change the thermodynamic conditions, for instance, you get closer to the spinodal, what happens is that the nucleation process take place faster, so you develop much more bubbles, which are much smaller than the previous one. So now, at changing the thermodynamic state, we can follow the nucleation of many or even a huge number of bubbles into our system, and then out of them, we can do some sort of analysis. So for instance, at changing time, so at increasing the time, we may count how many bubbles we are forming in the system. And from that, we have access to the nucleation rate. The nucleation rate is defined as the number of bubbles that you form per unit time, unit volume in the system. So the number of bubbles versus time is shown in the plot on the right. And you see that initially, the number of bubbles grows linearly with time until, given to the constraint on the volume, the system, as the bubble develops, gets compressed. So the number of bubbles that nucleate per unit time 10 degrees until a maximum is reached. And then another kind of dynamics takes place. Now, if we focus on the initial state, from the linear trend of the number of bubbles with time, we can extract from that the nucleation rate. So we have a way to measure the nucleation rate in the system, in the bulk system, depending on the thermodynamic conditions. We can do more than that. For instance, we can try to analyze what is the fate of the bubble. So for instance, what is shown here is the histogram of the volume of the bubbles normalized with the critical volume. And what you see is that, of course, initially you form a large number of very tiny bubbles, then the system evolves, and then you see that the average size of the bubble increases in time, until the population splits into two subpopulations. So we have a bimodal distribution. So one question to ask is what is the dynamics behind this kind of development? And if you try to follow what is happening along the simulation, you see that the bubble grow large enough, they interact and they start to merge. So what happens is that by the interaction of the bubble, by the merging process of the different bubbles, we are going to produce a subpopulation of gigantic bubbles, which are much larger on average than the other ones that you have nucleated a short time before. Okay, so this is the general picture. Now we want to be a little bit more quantitative. So we want to see what is the dynamic of a major bubble. So up to now, we have been focusing on the small scale dynamics of the system related to nucleation. But once the bubble has grown enough, large enough, then we should see the typical signature of the nonlinear dynamics of a grown bubble. So we have an equation for that, which is the Rayleigh-Plesset equation, which describes the time evolution of the radius of a bubble. And what you see in this plot on the right is the time history of a single bubble, which was isolated from the overall system, and that the radius at different time instant was compared with the solution of the Rayleigh-Plesset equation, the dots, the colored dots over there, and you see that the correspondence is complete. So this means that once the bubble has reached the major state, has grown large enough, then what you see is the actual nonlinear dynamics that you expect from a grown-up bubble. In the meanwhile, in the early stage, you see that the radius of the bubble grows according to a certain law, and you can compare this growth rate of the radius with what you expect from the string theory for the transition. And also in this case, you have a very good agreement. So this means that indeed the system is able to encompass the dynamics from the nucleation stage up to the grown-up nonlinear stage of the bubble. Now, if we want to get closer to a realistic configuration, of course, we had to include the interaction with the wall. So we had to deal with wall wettability. To include the wall wettability in the model, what we need to do is to modify the free energy functional by including a term which accounts for the energy of interaction within the fluid and the solid wall, which is the last surface integral on the top part of this slide. If you look for the equilibrium conditions, we have to now minimize this augmented modified functional. And then, of course, you obtain a different set of Euler-Lagrange equation. The first one is exactly identical with the one we had before for the bulk fluid. And the second one comes from the wall, from the presence of the wall, and it provides a boundary condition for the density field in terms of the free energy density related to the wall. Now, by manipulating this wall free energy, we are able to control the contact angle of the bubble. In particular, what you see here on the right, the top part on the right, is a case for which we have an hydrophilic wall. So consider that the water is outside, the liquid is outside, whereas the vapor is inside. And below, we have a case in which the surface is liophobic or hydrophobic, if you prefer. On the left, you are going to have shown a sketch of the density field in the system with the level lines of the density, which are intended to convey the idea that we do indeed describe the equation for the equilibrium contact angle, so the Young's equilibrium contact angle. So by manipulating the free energy, the wall free energy term, we are able to change the contact angle. Now we can include this model in our dynamic equation. And what you see here is a snapshot of bubble configuration along the nucleation process in a slab of liquid, of metastable liquid, between two solid walls. In this particular case, the wave stability was neutral, meaning that the contact angle was 90 degrees. And you see that indeed the presence of the wall favors the formation of the bubbles, such that almost all the bubbles that are formed grown attached to the upper and the lower wall. Now we can keep on proceeding with that and try to describe more complicated configuration. So in this case, what is shown here concerns the negation confined into a prism, a rectangular region. So this simulation took inspiration from another process, which is related to an apparatus that you find on the leaves of the fern, which is called the sporangium. So the sporangium is depicted in the top left part of the slide. You see that there is an inner part where the spores of the fern are contained. So the purpose of the sporangium is to keep the spore inside this sort of cavity until the conditions are mature for sending the spore out in the wind. So the sporangium overall acts as a sort of catapult, which ejects the spore into the free wind. This sporangium is formed by a sort of external annulus in which you see a sequence of square cavities. Those square cavities are bounded on top by a lid which is made of a permeable membrane, and inside each one of those chambers there is liquid water. Due to the sunlight, those water evaporates to the upper lid. As a consequence of that, the pressure inside each one of the chambers decreases, and this decreasing pressure deforms the elastic structure of the annulus, which becomes deformed and stores elastic energy. While the evaporation process keeps on going, the pressure continues to decrease inside the chambers until the threshold is reached, at which bubbles form in the chambers. When that happens, the pressure recovers, and as a consequence, the elastic energy stored in the annulus is released. So the annulus opens up and then launches the spore in the free wind. What you see in the middle is a movie taken from an experimental result, experimental model built by one of my former students, Andrea Montagna, in collaboration with Professor Barbara Mazzolai, in which by using two-photon microscopy, they were able to build an elementary model of one of these chambers. So you see a small chambers, you see the bar there, which accounts for 25 micrometers. And then on top of that, you have the lid. The water inside evaporates. And then what happens is the following: the membrane deforms, the pressure inside decreases. It decreases until all of a sudden, you have the nucleation of the bubble and the release of the pressure. Now, on the right, what you see instead is our simulation. So what we do, we have this cavity, we have a lid on top of it, we apply conditions such that there is a flux of water from the top lid related to the chemical potential difference between the inside liquid and external environment. So progressively, the pressure inside the cavity is decreased until you form the bubbles. Now, the nice thing that you see there is that those bubbles are formed right at the edges, at the corner of the cavity, whereas in the experiment, you see that the bubbles is mainly in the center. Of course, this is the initial stage. And if you know a little bit of theory about nucleation, you know that indeed bubbles should form at the geometric discontinuity. Then what happens is that those small bubbles, they coalesce and form the central bubble that you see in the experiment. And of course, the camera used in the experiment was not fast enough to follow all the initial details of this extremely fast process. Okay, now, once we have done this, we can keep on going by looking at the nucleation process induced by flow motion. So in particular, what you see here is a channel flow. So it is the flow of a metastable fluid between two parallel solid walls. The fluid is metastable. There are thermal fluctuations. Those thermal fluctuations trigger the nucleation of bubbles. You see that most of the bubbles are nucleated right at the walls, as it should. What we wanted to see here was the effect of fluid motion, in particular the shear flow or the shear rate on the nucleation rate. What you see in the diagrams in the lower part of the slides are the mean velocity profile for different conditions in terms of initial density, while on the right you see you compare the mean velocity profile as a function of the diffractability of the wall changing from lyophilic to lyophobic. So once you have this result, you may want to analyze them in a little bit more detail. So what you see here on the left is one of the walls of the channel, and those small light dots that you see are the embryos of the bubbles, so the critical nuclei. And those critical nuclei on the right are analyzed in terms of a Voronoi diagram. So what we wanted to see was the statistical distribution of those cavitation nuclei. So basically what we do, we build this Voronoi oscillation, and of course where the area of the Voronoi polygon, or the Voronoi polygon is larger, it means that locally there is a less dense distribution of nuclei. Where the area decreases, the density increases. So we can build an histogram of the sizes of these Voronoi polygons, and then compare them with statistical models for nucleation. In particular, one may expect that the spatial distribution of cavitation nuclei could be described by a Poisson process, and the distribution of the area of the Voronoi polygons for a Poisson process is shown by the solid line. So you see that the symbol more or less follow quite precisely the Poisson model prediction, but there are slight deviation at very large and very small areas. So this means that there is a certain tendency to clustering, meaning that there is a certain probability that where a bubble has already nucleated, there will be another bubble nucleating very close. The deviation is not extremely strong, but it's clearly visible in the result, in which the sides of the symbols correspond to the statistical accuracy of the data. The slide is divided into two columns. On the left column, you see the result for a quasi flow, which is a flow which is driven by a mass force, constant mass force acting along the axis of the channel, whereas on the right we are giving the result for a wet flow in which there is no force acting, except that the top and bottom wall, they move at constant speed in opposite directions. The histogram that are shown over there count the number of bubbles that you nucleate at different distances from the wall. And then you see that basically in these conditions, for the blue case, for which the density of the metastable liquid is 0.48 in reduced units, then what happens is that most of the bubbles are nucleated right at the wall. And this is true both for the wet flow and for the quasi flow. If you decrease the density, this means that you are favoring the nucleation, and then you see that the nucleation will start to be very important also in the bulk of the channel, are shown by the red bars in the histogram, which correspond to the metastable liquid density of 0.47. So I think that I'm almost running out of time. So I was expecting to deliver a talk for about 45 minutes. So if you have are patient a little bit more, I have a few seconds to spend. Let me comment on the conclusions. So once you have a system like this, again, you can count the number of bubbles that you develop as a function of time. And in particular, you may distinguish the bubbles that are nucleated at the wall from those that are nucleated in the bulk. And from that, you can extract a certain kind of conclusions about the effect of the shear on the nucleation rate. The preliminary conclusion of this set of simulation is that indeed the shear has an effect on the nucleation rate, and it tends to increase the nucleation rate. However, we consider this result still very preliminary, and the reason for that is that we see a different behavior between the Poiseuille flow and the Couette flow that we do not completely understand at the moment, and for sure needs a little bit more of investigation. So let me come to the conclusion. So in summary, we have been developing a stochastic system of partial differential equations used to model bubble-bubble nucleation. So this model takes contribution from different parts. So there is what is called Landau-Lifshitz fluctuating hydrodynamics, which corresponds to the fact that we have included the noise term into the deterministic equation. There is van der Waals capillarity inside, and of course there is the background of the Navier-Stokes equation. So the model consists of two parts: a deterministic component, which accounts for the phase change, including the latent heat of condensation. The deterministic model can take care of compressibility effect like compression waves and shock waves, and it accounts for the transition to and from the supercritical state. So this is important in the case of the collapse of bubbles, because the collapse is so fast usually that the system does not have enough time to transition from the bubble to the liquid state under compression. So what happens is that instead the transition to a supercritical state, it becomes incondensable, and then it sort of acts like a pneumatic spring. So what you're going to have is that during the collapse of the bubble, there is the high density fluid which is focused toward the center of the bubble, and then this sort of elastic spring suddenly stops this motion of the liquid toward the center, and associated with that there is a strong compression of the liquid which is reflected back and induces a system of shock wave which launch the wave from the center of the bubble. This for what concerns the deterministic part of the system. During this very intense processes, what you have is that you reach extremely high peaks of temperature and pressures. And then if you are in presence of a wall which breaks the symmetry, the spherical symmetry, then what happens is that you produce a strong jet which is responsible for the damage of the material. At present, we are running a couple simulation of this system together with elastoplastic model for the solid wall in order to simulate the damage that this impinging high-speed jet has on the solid wall. This has concerned the deterministic component of the system. There is the stochastic part. The stochastic part accounts for the bubble nucleation and allows to model the correct nucleation rate at changing thermodynamic conditions. Characteristic of the entire system is that we can reach unprecedented time and length scales, in the sense that if you want to deal with nucleation, the standard tool for doing that is molecular dynamics. And molecular dynamics means that you have systems which at most could be a few tens of nanometers in size, and then you have the time scale which is extremely limited due to the fact that the integration time scale is on the order of picoseconds. In our case, we can reach much larger length scale and time scales, up to the point to reach the macroscopic scale at which you see that the dynamics of the bubble follows the prediction of macroscopic theories. Very important is the fact that we can now couple nucleation with dynamics. That is, we can deal with flow-induced cavitation, which is something that at present was not possible with other models. So let me conclude by acknowledging the collaboration with Mirko Gallo and Francesco Magaletti. Both of them were my former PhD student. Mirko Gallo at the moment is a postdoc in my group in Rome at the Department of Mechanical and Aerospace Engineering, whereas Francesco Magaletti, since a couple of years moved to the University of Brighton in UK. I also wanted to acknowledge the support from the funding agency, in particular praise was very generous in providing us with computer times. So all the simulation that I was discussing were performed on the Marconi 100 system that we have available at Sinega in Bologna. And then I want to acknowledge the ERC for the grant that I got in 2013. At that time, I had a sort of dream of doing this kind of simulation, so I started a part of the project in this direction. It took us a little bit of time in order to reach a maturity state such that we could really do important simulation in this interesting field. So with that, I can conclude, and I thank you for listening, and I will be my pleasure to take questions if there are any. Thank you.
Thank you very much for your talk, your interesting talk, Professor Casciola. If there's any questions for our speaker, please raise your hands so we could direct it to him. Vangelis, please go ahead.
Yeah, if I may ask. So thank you very much. It was very, very interesting and very exciting for a very challenging problem. So just a couple of questions, let's say, more for me to understand. So first, I would expect that if you, let's say, were able to go to infinite time, then you could observe a single bubble. I mean, after a long time, there should be coalescence of all these bubbles in order to minimize the surface tension in the system. Am I right or not?
Yeah, in principle, you're right, in the sense that, you know, the point is that more generally speaking, we are considering a system which has two locally stable states. One of them is the metastable liquid, whereas the stable state is the full vapor. So if you wait sufficiently long time, the entire system will completely vaporize, unless the thermodynamic condition change. Okay, this process is only limited by the fact that we keep the system under the constraint of a fixed volume. As a consequence of that, what happens is that while the bubbles form, the liquid is compressed, so the local thermodynamic state of the liquid changes, the density changes, in particular the density of the liquid slightly increases, and that keeps the liquid farther away from the transition. So you are going to reach a sort of intermediate equilibrium state at which there will be a part of the system which will be kept in the liquid state, which will be no more a metastable state in presence of bubbles. Now, given the pressure of the system, there will be a typical size of the equilibrium bubble. So you should not think that in general, a big gigantic single bubble would be there, because such a gigantic bubble will be not in equilibrium with the environmental pressure in those conditions. So what I would expect, and what we see, is that indeed, after a while, the number of bubbles stabilize. I think I have a diagram showing that. I'm not sure, but so you see here, the trend is not completely clear because, of course, the number of bubbles is decreasing slowly, but there is a trend toward a stabilization of the number of bubbles.
And is there a specific power law that is followed during this stabilization, as you call it, or coalescence, let's call it?
We are not investigated that in detail. Probably there could be, but we didn't do that at the moment.
Okay. And if I made one more, so in the second part where you have the interface, the interaction, actually, you have a system that it's the nucleation happens at the interface. So if I understand well, in this macroscopic description, you see the interface, we describe the interface as a 2D area, let's call it. But in the microscopic level, typically what we see is that the interface is a finite region where the density is changing. So it's not arbitrarily modified, let's say, from the solid to so there is an area where the density is changing, and also the roughness play a very important role. So do you consider that this phenomena can affect the nucleation?
No, in principle it should. In principle it should. The point is that, you know, in order to account for that, I mean, you are talking of depletion layers and stratification of the wall or something like that, right? So what you're going to see, what you see from, say, molecular dynamic simulation, is that you have an oscillating behavior of the density close to the wall.
Exactly.
And that is, of course, it could be important for the nucleation process. The point is that in order to be able to describe that, the detail of the theory that we have been using is not sufficient. You have to go to what is called the density functional theory to do that, which in principle could be done. But then instead of having partial differential, stochastic partial differential equations, you're going to have integral equations, which means that the computational burden becomes larger and larger. So in principle, that could be done, but we didn't do that. What I can add is that in another context, where we were looking at the nucleation close to the solid interface, or we were more interested to the nucleation at the interfaces between oil and water, we find that indeed the interface act as a strong nucleation site.
Okay, yeah, you're right. Yeah, I was thinking even in a simple, let's say, extension to use a different boundary condition there, coming from the microscopic simulation.
Well, you know, the point is that in principle you could do it, but then the point is that if you want to follow those oscillations, it's a matter of numerical resolution. So already the system is quite demanding in terms of resolution. So although in principle it is at least thinkable, in practice it would be very hard to do this kind of time-dependent non-equilibrium simulations for that case.
Okay, thank you very much.
Nicola, you have a question?
Okay, thank you for your presentation. It was very, very interesting. So maybe a more elementary question from my side is, if you have a constant volume and also the density is changing, how does the mass is conserved? Maybe I didn't understand something.
You know, the point is the following. You start with the liquid, right?
Yeah.
So you have a liquid at a certain density. Then you form a vapor bubble or many vapor bubbles. So in the volume occupied by the vapor bubbles, the density is lower. So it means that the liquid gets compressed. So the density of the liquid increases. And overall, you conserve the mass.
Okay.
Does it answer your question?
Yeah. And another question, if I may. So what is a typical size of those boxes for your simulations?
Yeah. So for instance, this one, this cube over there is of the order of half a micron cubed.
Okay, thank you.
Okay.
Thank you.
So we in principle we can increase the size. That depends only on how big the machine they make available to us.
Okay.
Okay. So for the moment, at the moment, for instance, we are running simulation in which we have bubble of, I believe, order of 3-4 micrometers. So it means that the size of the domain is more or less at least 10 micrometers.
Okay. Okay. Thank you again.
You're welcome.
Thank you, Nicola. Is there any other questions for Professor Casciola? Anyone else for questions? Okay, I don't see any more. In which case, I would like.
There is one of Nikos.
Oh, sorry. Nico, go ahead.
Yeah, thanks for the interesting presentation. I have two questions. What is the added computational overhead with the new terms that you have added? And the other one is something that I might have missed. So since you do not go down to the molecular scales, how do you choose the nucleation sites? Is it just you start with a random distribution and then this part of the initialization process, or?
Okay, so I will start from the second question and then go back to the computational overhead. Okay, so you see from, let me find the proper slide. Okay, so you see here, basically what you have is a sort of extended Navier-Stokes equation in which you have these capillary terms added, and then there is those noise term, right? So what happens is that the intensity of that noise, that depends on the size of the grid. Okay, so the idea is the following. if you go back to the statistical mechanics description, you see that if I take a box which is very, very large, okay, the fluctuations in the number density become small. So we more or less have always the same number, the same number of particles inside a large domain. Whereas the more we reduce the size of the box of the cell that we have there, the more the fluctuation in the number density and in the energy as well becomes large. Okay. So what happens basically is that first of all, you have to fix a grid size that you think is sufficient. In particular, for us, the criterion is based on this the thickness of this diffuse interface layer over here. So in this slide, what you see pictured is the transition from the vapor to the liquid across the interface. So this interface has a certain thickness, and that thickness is a physical thickness. So it's not the free parameter. The reason for that is that if you take this van der Waals model, and then you fix the surface tension that you want to model, as a consequence of that, there are no more free parameters except the capillary number, the capillary parameter lambda there that can be used to tune the surface tension. And then the sides, the width of the interface is fixed. Okay. Now, the width of this interface is physical in the sense that this is physically sounded, and it means that this is very, very extremely small. Is a nanometer or less. Okay. So this sets a limit on the sides on the largest grid size that you can use. Okay. So we have a fixed minimum grid size that we have to take, and then we can make the system larger by increasing the number of grid points. Now, once you have fixed the size of the box, the intensity of the noise is determined by the equilibrium statistical mechanic properties, and then you fix the noise. Once you've done that, the system goes automatically to form the bubble. So the noise over there, where was the equation with the noise? The noise over there start to force the momentum and the energy equation. As a consequence, the density start to fluctuate, and you produce local variation of density. When this local fluctuation of density randomly take place on a scale which is larger than the typical nucleus of the bubble, which is set by the thermodynamic conditions, say by the pressure and the temperature, local pressure and the temperature, then you form a true bubble. So the bubble start to expand and becomes a mature bubble. So it's no more reabsorbed, and it stays there. Okay, so this is the mechanism by which you form the bubble in this system. Now, when it comes to the computational overhead, basically, I wouldn't talk about overhead as such. So the system is basically nothing else that a complicated system like Navier-Stokes equations. So in principle, you can use algorithms which, for instance, many of the results that I was showing were computed using central finite differences. Other ones were calculated by using a spectral method. So the method used in general is not so important. What really matters is the possibility to make this computation highly parallel. So for that, the different numerical algorithms, the different discretization that we were adopting from trying to find the best compromise for solving these equations were implemented using the PET-C library, which allows to solve this kind of problems by using efficiently the parallelism of GPU accelerated systems.
Okay. Okay. Thank you.
You're welcome.
Thank you, Nikos, for your question and your answer, Professor. Anyone else with a question? Anyone else? No, I don't see any again. In which case, I would like to thank everyone for joining today's seminar. And most importantly, I would like to thank Professor Casciola for being our speaker today and presenting his work. I'm sure that he will be able to answer any questions if there are any follow-up questions.
Let me just show the address such that if somebody wants to send me an email for asking questions, I will be more than happy to try to answer. So thank you again for the invitation. It's been a big pleasure talking to you tonight.
Thank you for being our speaker. Yeah, we'll see everyone again at our next seminar.
Okay.
Thank you and bye-bye.
Thank you very much. Thank you very much.
Goodbye. Bye.
Bye. Bye.
Bye.